The next lesson we're going to talk about is partial fraction decomposition. For those of you moving into calculus, you'll find this becoming more of a topic in calculus 2 rather than in calculus 1. So what is partial fraction decomposition? Well, we know the sums of rational expressions are found by combining two or more other rational expressions into a single rational expression. So what partial fraction composition does is it decomposes that singular rational expression into the sum of all of its components. So given one rational expression, we want to express it as the sum of two or more rational expressions. So we call this special type of sum a partial fraction decomposition, where each term in the sum is called a partial fraction. So if we look at a sum, say 3 over x plus 4 plus 2 over x minus 3, we know from the fact that we have practiced adding fractions since the last exam that we can find a common denominator, and then we would multiply each fraction by the missing piece of the denominator in order to combine them into a single fraction or a single rational expression. So the way that that shows here is we took x plus 4 and x minus 3. They have nothing in common. Those are two separate linear binomials that do not have the same expression. It's not like we have x plus 4 and x plus 4 squared. We just have x plus 4 and x minus 3. So their common denominator would in fact be x plus 4 times x minus 3. And what we would do then is we would multiply the 3 over x plus 4 by x minus 3 over x minus 3. And we would multiply the 2 over x minus 3 times x plus 4 over x plus 4. And where does that end up? That means we end up right here with 2 times the x plus 4 in the second half and 3 times x minus 3 in the first half, in order to get us to be over x plus 4 times x minus 3. And when we combine like terms, we'd get 3x plus 2x is 5x. Negative 9 plus 8 would give us negative 1. So the other way we can remember this one is we can remember that if I have a over b plus c over d, I can combine those to get a times d plus b times c all over b times d. It's a quick formula that will help remind us how we can add fractions. Now, this will become more complicated if we have more than two, but it's the same idea. And we'll practice a little bit of all of these kinds. So could we actually decompose 5x minus 1 over x squared plus x minus 12 back into its separate components? The answer is we will, but we're going to try a couple of different examples first. We're going to start with a pretty simple, straightforward one. We're doing one that's a little more complicated, and then we're going to get back to this one, and then we're going to wrap up with a challenge question. So let's talk about the partial fraction decomposition of 4 over x squared minus x. Well, first things first, we want to rewrite this in factored form. So this would be 4 over x times x minus 1. And once we have it in factored form, we now know that our two different possible factors for our denominator would be x or x minus 1. What I'd like to do is go ahead and put those two factors together to equal our 4 over x times x minus 1. So we'll say let's break down 4 over x times x minus 1 into, let's say maybe, how about a and b would be our constants? Let's make it a over x, and let's do b over our x minus 1. And what we know about equals the idea of equality in mathematics means that whatever is on the left has to equal whatever is on the right. So what we're going to do, there are two ways you can accomplish this. You can multiply both sides by the common denominator, or you can go ahead and combine those fractions together on the right-hand side. And then when they have the same denominator, the concept of equality means that their numerators also have to be equal. They are two sides of the same coin. I'm going to show you the way that I do it, which is I put all of it together and then I say since they have the same denominators and they're equal, that their numerators must be equal. So we're just going to take our 4 over x and x minus 1, and we're going to combine our terms over here in the way that we would if we put them over the same denominator, which would be a has to be multiplied by x minus 1. And then b would be multiplied by what it doesn't have, which is x. And this is all divided by x and x minus 1, which means by the definition of equals or equality that 4 has to equal a times x minus 1 plus b times x, right? And the way these go together then is we're going to do something called equating coefficients. So we're going to talk about equating coefficients, but first let's simplify. So here we could either find the combined fraction or multiply by the common denominator. Or multiply by the lowest common denominator here. In either case, you would end up with 4 equals a times the quantity x minus 1 plus b times x. So I'm going to move the a's and b's to the left and set it equal to 4 because I'm going to add a little bit to what is there with the 4 once we break down a little bit more with what's with the a and b. So what we have left here is a times x minus 1a. We're going to add to that b times x. And you notice we have terms that are x's and terms that are constants. So on the other side, what's going to be really important to say is that we know we have 0 x's and we have a 4. And the reason being, we're going to go through this process next called equating coefficients. So equating coefficients means that whatever is on the left has to equal what is on the right. So no matter how many x's or in what form I have my x's on the left, they have to equal the same number of x's I have on the right because they're not coming from anywhere else. The same is true if we had x squareds, x cubes, or even the constant. So if that's the case, let's put them together. So first things first, let's find our x's. I have ax plus bx. So let's just factor out an x, and I am left with a plus b. Right? And then let's put together just our constants. Well, our only constant is the negative 1a, or if you just had negative a, that's fine. So we just have minus 1a. And on the other side, we have 0 x's. Oops, I started to write a q. Let's change it back to a 0x plus a 4. So what equating coefficients means in this case is that on the left side, I have x's that have a coefficient of a plus b. Meaning that once I know what a and b are, I'm just going to add them up, and that's how many x's I have on the left. Well, in order to be equal to what's on the right, they have to add up to 0. So I would say in terms of x's that I have a, oops, let me put it in the right color. I would have, here we are, a plus b And on the right, it equals, well, we don't have any x's, so it would be 0. And then we look at our constants, right? Our constant coefficients are just a negative 1a on the left. But on the right, it's equal to 4, which means I can solve for a right away. Because if I know negative 1 times a is 4, that makes a negative 4. So I can solve for a right away. A is now equal to negative 4. Well, that's great because then I can come back up here, and now that I know what A is negative 4. Well, negative 4 plus B has to equal 0, right? So that makes B 4. So B equals 4. So where we end up in the end is now I know what A equals and what B equals, but remember where we started. We started back here, so what we want to do is rewrite it then. So in the end, what we have is that 4 divided by x times x minus 1 is equal to A, which is negative 4, divided by, well, what term did we put with that one? We put x. So it is negative 4 over x plus, and then B was 4. And with that term, we had in the denominator x minus 1. And that would be our partial fraction decomposition. If we wanted to make sure that we didn't make an error, we can multiply the right-hand side back and see if we get 4. Right? We could find the common denominator on the right and make sure the numerator is 4 once we combine it all together. I will say I made a couple of errors when writing out my own answer key, and the check really helped me to figure out that something went awry. It doesn't exactly tell me where, but you can sort of figure it out if you look through your work. And you can say, I ended up with 8x when I should have had 4x, so I have 4 extras. What happened? And usually it's in our equating coefficients step that we accidentally equal it to a wrong coefficient. When it should be 0, we accidentally make it the 4 for this one, okay, for example. So let's do a quick check. We'll do that. Let's do a quick check. Well, let's see here. So negative 4, my other pens. Negative 4 times x minus 1, right? Plus, there we go, 4 times x minus 1. Let's see what it equals, right? Because that's how we would get our denominator, right? This would all be, oh, that one should just be times x. Sorry about that. And this should all be over x times x minus 1, and it should equal 4. So the question is, does it? Well, let's see here. So we would end up with, let's see here. Let me find you a different color. There we go. So let's do negative 4x plus 4 plus 4x. Does it equal 4? Well, those x's sure cancel out. 4 does, in fact, equal 4. So we are good. Okay? So when in doubt, run a check. Make sure you got the right answer. Okay, let's try a slightly more complex example here. So for this one, I have x divided by x squared minus 5x plus 6. Well, what multiplies to give me 6 and adds to give me negative 5? Hopefully negative 2 and negative 3. So let's do x minus 2 and x minus 3. If you did x minus 3 first and then x minus 2, this would also work out just fine. It's just that what I say is A, you will say is B. What I say is B, you will say is A. In the end, we're going to find the same decomposition, okay? So if I have x divided by x minus 2, x minus 3, that means my decomposition came from an x minus 2 term and an x minus 3 term. And so once again, our numerators will be A and B. Okay? So we're going to see what A and B could possibly be. So let's find our common denominator, put it all together. So we know that x over x minus 2 and x minus 3 would equal. Well, in this case, we would have A times x minus 3 plus now we would have B times the other term, which is x minus 2. And it's all over x minus 3 and x minus 2. So now that their denominators are the same, we know that their numerators have to be equal. And so we know then that A times x minus 3 plus B times x minus 2 has to all add up to x, because that is what's left over on the left-hand side. So if we start doing a little simplification here, we would have, let's see here, we'd have ax minus 3a plus bx minus 2b. And it has to all equal x. And remember how combining our terms together helped us on the last example? We're going to do the same thing before we equate coefficients this time. So let's move all of our x terms first. So here we would have ax plus bx. So we're just going to move that first, ax plus bx. And then we had minus 3a and minus 2b. Okay, and now let's just factor out our x, and we're left with a plus b. And now we add to that our constants, and I'm going to put those just in a set of parentheses so we can find them a little more easily when we're equating coefficients. It's not necessary, just helpful. And now it equals x. But notice what we don't have on the right. On the left, we have terms in terms of x, and we have constants. But on the right, we only have x. So what we're going to say is then let's add to that a 0 for our constant to remind us when we start equating coefficients what we're setting it equal to. If that term does not exist on the other side, it is equal to 0 of them. So let's see where we go from here. Let's talk about our x's. I have to go up here so we have some space, okay? Let's talk about our x's. Our x terms are a plus b. Right, a plus, let me find the right color, b. And that equals our x's on the right, which is just the 1x. And then if we talk about our constants, now things look a little different. We have negative 3a minus 2b. And that one doesn't have something to equal on the right-hand side, so we're going to set it equal to 0. And this is where our study of linear systems comes in very handy, because now we can use elimination to help us figure out where to go from here. So from here, if we wanted to eliminate, say, b, we could multiply the first equation by 2 and leave the second equation alone. We'd end up with 2a plus 2b equals 2, and we'll leave our negative 3a minus 2b equals 0. And let's add them up. Well, the 2b's cancel out, and now I'm left with negative 3a plus 2a is a negative a, and it equals 2, which means that a is negative 2. And once we know that a is negative 2, we can solve for b. So b is negative 2 plus b, and that equals 1. Well, that means b itself would then be add 2 to both sides. B is 3. So now we know that our decomposition is that x over x minus 2 and x minus 3 can be broken down into a, which is negative 2, over x minus 2, plus b, which is 3, divided by x minus 3. And that is our partial fraction decomposition. And once more, you can multiply the right-hand side to double check that it does equal the left-hand side. And when we do negative 2 times the quantity x minus 3 plus 3 times the quantity x minus 2, we do indeed get back x. So if you wanted to see the check, I can do that over here on the right. And we'll do that here. We'll do it in blue. So here's our check. We would have negative 2 times the quantity x minus 3 plus 3 times the quantity x minus 2. And we want to know, does it equal x? I'm running out of space there, but we'll just put that way. So we get negative 2x plus 6 plus 3x minus 6. Does it equal x? Well, 6 and 6 cancel. Negative 2 plus 3 is indeed x, so it does check. So our work is sound. We're now going to circle back to the problem we began with, which was, can we break down 5x minus 1 over x squared plus x minus 12 back into its separate components, which is where we began. So let's see how this would break up. So we know that 5x minus 1 is staying our numerator, but we know that we can factor the denominator. Well, what multiplies to give me negative 12 and adds to give me 1 would be a negative 4 and a positive 3. So we'd have an x minus 4 and an x plus 3. Does that sound right? Oh, nope, that would give us a negative x. But this is the same kind of problem that I see happening a lot on these problems. And it's the same thing that I have seen students do in class multiple times. So just take one more quick peek at it before you start doing all your work and make sure x minus 4 times x plus 3 would give us x squared plus x minus 12. It does give us the minus 12, but it gives us a minus x. So instead, we need to change these to be an x plus 4 and an x minus 3. So now we have a positive 4 and a negative 3. When we add those, we'll get the positive 1 we were looking for. So just a reminder, mistakes can happen that easily. So make sure that you double check that your denominator is correct before you move on. So now we'll go ahead and move on now that we've double checked, because we know 5x minus 1 over x plus 4 and x minus 3 now has to equal some factor a, right? Some value a over x plus 4. And we're going to add to it some value b over x minus 3. And we know then that the common denominator would be x plus 4 and x minus 3. So what we're going to say then is that on the left we're going to have, I'm going to go ahead and switch the sides like I did last time, a times x minus 3 plus our b times x plus 4 has to equal what's left of our numerator on the left, which is 5x minus 1. And again, at this step, double check that you wrote the same thing, that you wrote the same signs that you already had in your problem. Just make sure they're still there. So let's continue to simplify. We have ax minus 3a plus bx plus 4b. And we know it has to equal 5x minus 1. Let's do the same thing as before, move all the x's together. So we have ax plus bx That makes things pretty easy. It's an a plus a b. Right now, let's move our constants together. So minus a 3a plus a 4b. And this all has to equal 5x and minus 1. Now, the nice thing is we do have an x term and we do have a constant, so neither of those will be 0 this time. Let's combine and factor out those like terms. So we have our x times our a plus b. And then for our constants, again, I'm just going to put them in parentheses like we did before, just to make it easier to find. We get negative 3a plus 4b. And this all equals 5x minus 1. So if we equate our coefficients in terms of x's, on the left we have an a plus a b, and it has to equal whatever coefficient x has on the right, which happens to be 5. So we have this 5 right here, so we'll set it equal to 5. And if we look at our constants, we have negative 3a plus a 4b, and it equals its constant, which is negative 1, which we found right over here is negative 1. So from here, we now have to figure out how to solve for A or for B. You can use substitution if you want. I'm going to stick with the way we've been doing our elimination when we have systems of equations. So I'm thinking that we could either eliminate A or we could eliminate B. But if I do A, I only have to multiply the first equation by a positive number, not a negative number. Don't have to worry about the signs changing. If we wanted to eliminate b, we could multiply the first equation all by negative 4. It would still work. It's fine. It doesn't matter. You know me, though. I'm just going to try to find the one that's the easiest to get through, which means let's multiply the first one by 3. What is our easiest way? 3a plus 3b equals 15. And then we'll leave the second equation exactly as it is, where we have our negative 3a, which those will cancel out, right? Plus our 4b. And it equals our right-hand side, which is a negative 1. So let's add it all up together and see what we end up with. Well, the a's cancel out. 3b plus 4b is 7b. And it equals 15 minus 1 is 14. B is 2, which tells us that A plus 2 has to equal 5, which means then certainly that A must equal 3. Oh, I think I put that in the wrong color. Let me fix that. We'll make sure it all makes sense and it all matches. There we go. Has to equal 5, which tells us, in fact, that A does, in fact, equal 3. So we can write our partial fraction expansion down as 5x minus 1 over x plus 4 times x minus 3 is the same as A is 3 divided by A was over x plus 4, and B was 2, so plus our 2 divided by our other factor, which was x minus 3. And that would be our partial fraction decomposition for this problem. If we wanted to do a check, we certainly can. We know that 3 times x minus 3 plus 2 times x plus 4 should equal our numerator of 5x minus 1, but does it? Well, 3x minus 9 plus 2x plus 8, does it equal 5x minus 1? Well, 3x plus 2x is 5x. Negative 9 plus 8 is absolutely negative 1. So we do get 5x minus 1 equaling 5x minus 1. So our work is out. For the last problem, we're going to challenge ourselves just a little bit more. Okay, on this problem, what we have is something called an improper fraction, and that is because the numerator has a higher degree than the denominator. So this is going to be a two-step solve on this problem. This is one of our challenge problems. If I have 2x to the fourth and I'm dividing it by an x cubed, I can use what we just finished learning about last class, which was polynomial long division, to help start this process of how I could rewrite this quotient. So let's set up our division first. So if we've got x cubed minus 4x, and we're dividing it into 2x to the fourth minus 8x squared plus 5x and minus 2. We need to start with our first term, which would be the, there we go, our x to the 2x to the fourth divided by our x cubed, which just gives us a 2x. So we have our 2x. Well, 2x times our x cubed minus 4x gets us 2x to the fourth minus 8x squared. If we multiply it by our negative, we get negative 2x to the fourth plus 8x squared. So let's plug that in. Negative 2x to the fourth plus 8x squared. Well, guess what? There's nothing left from those two terms, but I do still have a 5x minus 2, which would now be my remainder because it has a lower degree than our divisor. So what we're going to see here is we have a 2x plus a remainder, but we can factor that remainder. So let's figure out how to factor this remainder. The remainder here would be 5x minus 2 divided by our divisor, which was x cubed minus 4x. So now we went from a polynomial long division back to a partial fraction decomposition. So let's rewrite this first as 5x minus 2 over x times x squared minus 4. Well, this is where things get even more challenging because x squared minus 4 is an x minus 2 and an x plus 2. Now when we decompose, we're not going to have just two fractions, we're going to have three. So let's look at what this would look like. So we would say then that we've got 5x minus 2 over an x minus 2, and an x plus 2. And we're going to decompose this into a over x plus b over x minus 2. Make that red. There we go. And then we're going to add to it c over x plus 2. And now our common denominator is x minus 2, and x plus 2. So we're going to have to multiply both sides by that, or we're going to have to combine them all together to find out how we get to the same common denominator. So in this case, we end up with 5x minus 2 over x times x minus 2, and x plus 2 is now going to equal our a, and a has the x, but a does not have the x minus 2 and the x plus 2. So we're just going to have a, and it's going to be multiplied by x minus 2 and x plus 2. And then we'll have b, which has the x minus 2, but it doesn't have the x or the x plus 2. And then finally we'll have c, and it has x plus 2, but it does not have x and x minus 2. And this is all over our x minus 2, and our x plus 2. You would arrive at that same numerator if you multiply both sides by the common denominator, which is the x minus 2, and the x plus 2. You would end up with the exact same numerator. So what we're going to do is we're going to step outside of our long division there, and we're going to bring our work up here a little bit and say then, okay, so now what? So now I've got a x squared minus 4a plus I have, let's see, let's grab the right color, bx squared plus 2bx. And then for c, I've got cx squared minus 2cx, right? Ax squared minus 4a plus bx squared plus 2bx plus cx squared minus 2cx. And it all equals our 5x minus 2, which notice has no x squareds. So we're going to have to worry about that. So let's put in here no x squareds plus 5x's and minus 2. Let's put together our x squared. So we have ax squared plus bx squared plus cx squared. And then let's now add up our x's. So in terms of x's, well, first one doesn't have it, the second one does. We have plus 2bx, right? And we're going to add to that, oh, actually, we're not going to add, we're going to subtract 2cx. And now let's combine all of our, not combine, but collect all of our constants. So we have minus 4a, and that's it. There are no other constants. This bodes well for solving here in just a moment. So let's see, it's equal to 0x squareds plus 5x's and minus 2. And so this should help us in terms of solving because it looks like for our constants, we only have one on the left and one on the right in terms of terms. So it should make our lives a little simpler. Let's see if it pans out that way. Let's go ahead and let's collect our x's. And in our x's, we have our x squared, sorry. And these are our x squareds. A plus b plus c. And in terms of x's, we only have 2b minus 2c. And this is where the fun comes in. It's plus, then our only constant is a negative 4a. So when we start equating coefficients, I may actually start from the back instead of the front. I usually start with my x squareds and then my x's and then my constants. But in this case, we can see that there's probably a faster way to get started here. And that's that I only have negative 4a as a constant and 2 on the other hand side. I want negative 2. So let's do that. Let's start with our constants. So let's look at our constants. We have negative 4a equaling a negative 2, which tells me then that a is negative 2 over negative 4, so it's a positive 1/2. Wait, we can have fractions in a fraction? The answer is yes. Well, now let's look at our x's, because those are only in terms of b and c. But then now that we know what a is, we could also see that we have a way to get around this b and c in our x squareds. So we'll need a little more space, but we'll figure this one out. Let's put together then what's left. So we've got, in terms of x's, we have, find the right color here, 2b minus 2c, and it's going to equal, well, in terms of x's, it's going to equal 5. And if I look at my x squared, which is going to be the other fun one, we now know that a is 1/2. So we might have a little bit of work to do. So maybe we'll move it over here, x squared. We know a is 1/2, so I'm just going to drop in 1/2 here, plus our b and plus our c. And on the right-hand side, it just equals, well, 0. There are no x squareds. So it'll just equal 0. So what we can do now is we can multiply that entire equation by 2 so that we don't have to deal with fractions. So if we multiply that whole thing by 2, we know that that is 1 plus 2b plus 2c, but it still equals 0. And that's going to be a little easier to work with because now we could rearrange this to say that that is 2b plus 2c equaling a negative 1. And now, if we put that version with our version of our equations from the x's, we can use our elimination directly. So what we're going to do is we're going to combine this and this, the two stars together. So we're going to say, okay, I've got 2b minus 2c equals 5, and now I've got 2b plus 2c, right? 2b plus 2c, and now it equals just 1, or negative 1, I should say. And when we add it all up, let's see what happens. Well, the two c's cancel, and now I'm left with 4b equaling 4, which tells me that b is in fact 1. Well, that's a little easier even than having 1/2. Now we've got a 1/2 and we've got a 1. So all that's left is now we have to find c. So let's go back to our 2b minus 2c equals 5, and we now have 2b, which is 1, right, minus 2c, and it equals 5. So I put 2c in the wrong color. Let's see here. 2c. We'll rewrite it. There we are. And now it equals 5. So now I have 2 minus 2c equals 5, right? So, oops, grabbed the wrong color. Give me 1 second. 2 minus 2c equals 5, which means that negative 2c equals 5 minus 2 is 3. So c equals a negative 3/2. So we have c is a negative 3/2. We have that b is 1, and we have a is 1/2. All right, so now the question is, now how do I rewrite this partial fraction decomposition? Well, that would be, we would say then that, let me grab our colors the right way here. We would say then that we've got 2x to the 4th minus 8x squared plus 5x minus 2 all over x cubed minus 4x can be rewritten as, and we still have that 2x from before, right? 2x. And now we're going to add to this everything we found in the remainder. Well, a is 1/2, and it's over x. So 1/2 divided by x. Right? And then b was just 1. So it's just 1 over, we did x minus 2 next, I believe. Yes, x minus 2. And then c is a negative 3 halves, so I'm going to subtract my 3 halves over x plus 2. And while this is technically the correct answer, a lot of times you'll be asked to simplify this into 2x plus, and this would be a 1 half times a 1 over x, and this would be a 3 halves times a 1 over x plus 2. All we have to do is take that half and move it to the denominator on each one when we have halves. So this would end up being 1 over 2x, and then plus 1 over x minus 2, and then minus 3 over, and then it would be 2 times x plus 2, which can look a little deceiving in terms of where we started because it doesn't look like we have a 2 in there anywhere. So I personally, when I do partial fraction decomposition, it's typically in the setting of a Calc 2 class or differential equations class. And if I get fractions, I don't mind the fractions in the numerator. It doesn't bother me. However, in a lot of other applications, it might be easier to instead move the 2 to the denominator. So that will be up to your future teachers to help you figure out which version they want. Okay. So you can finish the first 5 problems on homework 16 with what we learned here. And I will say that challenge problem is not part of it. But I wanted to make sure for those of you moving on that you get a glimpse of what is coming in the future. The only other topic we really didn't touch on in this section was what happens if I have quadratics in the denominator. So that may be something new to pick up when you get to Calc 2 or to differential equations.